Welcome back, everybody. Today we're going to be once again asking the question of how does the fundamental theorem of calculus, part 2, generalize? And today we're going to be thinking about how it generalizes when we're integrating over a surface in space, something like this. Now, recall how we're thinking about the fundamental theorem, part 2. On one hand, we can integrate over something, adding up derivative information, or we can integrate over the boundary of that thing with some direction information and add up function information. Now, before we get to what Stokes Theorem is going to be telling us about surface in space, let's jump back to the situation where we were integrating over a plane or a region in the plane. And it was Green's theorem that was our generalization of FTC2 in this situation. And so recall the situation here is that we had some region in the plane, some D, and we also had a vector field going on, right? So we were imagining we had some fluid moving about the plane. Maybe this is like some cross section of a river or something like that. I don't know. We got some fluid moving around. So we got a vector field. And thinking physically, Green's theorem told us that we could either go through our whole region, adding up the circulation of our vector field at each point. And so this was the picture where we could go through every point in our region D and add up the circulation of our vector field at that point. Or, Green's theorem says, we could just march around the boundary of that region in the counterclockwise direction and figure out the circulation of F just around that boundary curve. And what I claim is that Stokes' theorem says the exact same thing. But we're going to take our region here and kind of toss it up into 3 space like a pizza and magically keep it suspended. And we have to be a little bit careful in order to grab these concepts here of the circulation of our vector field at our points and then the circulation of F around C. All right, but it's saying the exact same thing. Let's see what it looks like. Okay, so here it is in all of its glory. The surface integral of the curl of our vector field F over our surface S equals the line integral of our vector field F around our boundary curve. All right, so let's kind of pick this apart and look at the different players involved. So to start here, all right, we do have a vector field F. And again, this is kind of doing the same jobs it did before. We have some fluid, moving around in 3 space. So now we're imagining that we're like submerged under the ocean and the water is moving around. And so, at each point in 3 space, we have a green vector attached to it, showing us how that fluid is moving. Now we've also seen that when we have a vector field, the curl of that vector field is another vector field that's describing how our fluid is rotating, right? So the idea is, right, attached to, say, this point right here. We want to imagine that we have a fidget spinner, right, that we magically suspend at that point. and we want to see what direction it's rotating and how fast. And so here, given the green vectors for f, this thing's going to be wanting to rotate counterclockwise. And so thinking about the right-hand rule, the curl vector at this point would be, kind of pointing up this way, so that the right-hand rule gives the correct direction of rotation that our fidget spinner would have. All right, and we imagine here, and maybe at this point, we have another fidget spinner attached, and maybe it wants to orient itself like this, and maybe it also wants to spin counterclockwise, but maybe it's a little bit slower, so it has a little bit smaller of a vector, right? And so we imagine at every single point in 3 space, we can imagine having a fidget spinner attached and seeing how it's rotating, and then drawing that vector to represent that rotation. All right, so at every single vector, we also have a blue curl vector as well. Now, what I claim is that over on the right, this integral here is exactly handing us the circulation of our vector field around C. And it's doing that for the same reason that it did before, actually. Notice the right-hand side of both these theorems are the exact same. Right, it's just moving around the boundary curve, something like that, in the appropriate direction, which we'll talk about in a sec. And right, line integrals for vector fields add up tangential components, right? So like, for example, at this point right here, we'd have our unit tangent vector, and we would be grabbing the tangential component of our green f vector there, right? And that's what our line integral is adding up all around the boundary curve, right? So this line integral is physically computing the circulation of our vector field around our curve. And what I claim is that this integral on the left is going through our surface and once again adding up the circulation of our vector field on our surface at each point. And so here's why that is. So again, at each point, we have a blue curl vector attached to it, right? And so maybe at this point here, we attach some fidget spinner to it, and we decide that based on how it's spinning, this is its curl vector. Well, in order to see how much of that rotation of our fidget spinner is actually happening right on our surface, and we want to know how much of this rotation is actually happening on our surface. Well, with the tilt that it has right now, some of that rotation is kind of rotating off of our surface. If we want to see exactly how much of that rotation is happening on our surface, we need the normal component of our curl vector. Maybe I'll do it in orange. All right, so we have our normal direction, and we grab the normal component, and it's this normal component that's going to be describing the circulation that's happening at this point on our surface, right? This is kind of discounting any kind of circulation that's happening off of the surface. This is what's happening on our surface. And this is what our surface integral is going through and adding up, right? A surface integral for a vector field computes the normal components of the vector field. So this surface integral is going through, and at each point on our surface, looking at the curl vector and grabbing the normal component and adding those up. And so it's going through, in other words, our surface and adding up the circulation at each point on our surface. And so we really do have the exact same idea going on here with Stokes' theorem as we did with Green's theorem. Now, one subtlety here that gets added in when we're integrating over surface and 3 space is that with our 2 components, I guess, going on, one on either side of this equation, and what I mean is on the left-hand side, for this surface integral, we need a normal direction chosen on our surface, and over on the right-hand side, for this line integral, we need a direction of parametrization chosen for our curve. In order to get this equation from Stokes' theorem to work out, these need to be chosen in harmony with each other. And the way that that works is we want to imagine that once we choose a normal direction, that's somehow showing us, the above direction. And the idea being now, if we then look down on our surface from above, we want to be moving counterclockwise. And so here we can imagine with these normal vectors pointing up here, if we were up here looking down on our surface, this direction that we've actually drawn in would be moving counterclockwise. And so that's the correct choice of our direction of parametrization for our line integral. So our normal vectors and our unit tangent vectors here are working in harmony. Another way to think about this is that once you've chosen your normal direction, you can imagine a right hand being drawn. And if you slide that right hand around to the outer curve, that'll show you the direction that you want to be moving around it on. You can also see that with a little animation over here. So here we have a surface. It actually has 2 boundary curves. We're not going to worry about that. So here we have a normal direction chosen. Got the 2 boundary curves. So the normal direction, we can imagine with the right-hand rule, here it has a gear spinning according to the right-hand rule, and if you drag that gear to one of the boundary curves, that will show you the correct direction to be parametrizing that curve with. And so that's kind of a fun animation. Let's watch it one more time, shall we? So normal direction, the right-hand rule is going to give us a particular spin direction, and we drag that down. That's going to show us the direction that we should be moving along that curve. So that's the idea. All right, and so with that, let's put it to work. All right, so let's use Stokes' theorem to compute the surface integral for a curl field for this particular vector field, where our surface S is on this ice cream cone poking out along the x-axis. And so here we are given the orientation for our surface, and this is going to be showing us which direction our normals are going to be pointing. And so here it's pointing inward. So here you can imagine all the normal vectors attached to this ice cream cone. Instead of pointing to the outside, they're pointing to the inside. So we have this sort of orientation for our surface integral. Okay, well, the way that we use Stokes theorem is very similar to how we used Green's theorem in the past. We use it by immediately taking this surface integral for the curl field and switching it out for a line integral over our vector field, right, with the correct orientation. The language that's used is positive orientation, the direction that matches or is in harmony with our choice of normal direction on our surface S. And at this point, once we've taken our surface integral for the curl and swapped it out for this line integral, this really becomes our world. We can forget about the surface integral and we can compute this line integral just like we would any other line integral, right? We have our 2 steps for success. How do we compute a line integral? That's right. Step 1 is, right, we want to parameterize our curve with r hat, which in this case is going to be handing us x, y, and z, since our boundary curve is in 3 space. Our boundary curve here of our surface is this kind of the lip of the cone here. And once we parameterized our curve, then we just need to translate our integral. At this point, though, we don't know what direction we're supposed to move along our curve, right? We need to have the correct, the positive orientation. And so the question is, do we want to move this way along our curve C? Oops, I meant that to be in pink. Whoop. Or do we want to move this way along our curve C? And again, we can think about either one of these 2 ways. Ponder that just for a second, which one of these it's going to be. It's going to be this way. Right, you can imagine, if there was a gear right attached to this normal vector, for the right-hand rule, it would be spinning like this and sending us this way along the curve. Or if we imagine that, right, we have this normal vector is like stabbing us in the eye as we look downward, all right, then counterclockwise is going to be again moving this direction along our curve. So not this way, we want to move this way along our curve. Okay, so now that we know the curve that we're thinking about and what direction we want to move, why don't you pause the video, take some time, see if you can come up with the parameterization for our curve in the right direction, and then translate the line integral and compute it. All right, well, in terms of getting our parameterization, we need to describe our boundary curve. And what we can see from our picture is that this boundary curve is actually coming from cutting off our surface, our cone, at x equals 2. And so in order to describe this, let's figure out what that trace looks like, the x equals 2 trace of our surface. So if we combine our 2 equations here, x equals 2 and our surface, we get very quickly a nice equation for a circle centered at the origin and radius 2. All right, so here is the picture that we get in the YZ plane. But now, recall, we are not parametrizing a surface now, we're just parametrizing a curve, right? So we don't want this filled in or anything. We really just want this outside edge. And so to describe that in polar, if we want, we can just say, well, the radius is going to be 2 all the way around, and we can use angles from 0 to 2 pi to get the whole circle. And that's going to tell us how to describe our y and z in terms of polar, right? Y and z. We can swap out with what they are in terms of polar, r cosine theta for y, and r sine theta for z, right? Because y is the horizontal here, z is the vertical, and use the fact that r equals 2. So that gives us our y and our z. What about x? Well, where does that come from? Well, that comes geometrically from our picture up here. Right, our curve here lives entirely in the plane x equals 2. Right, that's where this curve came from. It came from cutting our ice cream cone at x equals 2. Or in other words, every single point of our curve here has its x-coordinate 2. Because of that, x is going to be 2 for every point on our curve, and we can just make that substitution. And so with that, we get a nice clean parametrization function, r hat, right here. And with that, step 1 of parametrizing our curve is all set. Now we just need to translate our line integral. And how do we translate a line integral? Using our mnemonic, right? We got our catchphrase. And I'm having trouble. What's our catchphrase? It's multiply by 1 over dt dt. Excellent. All right, and so if we make use of that, we're shown what we need to do. So I'll just bring this down. So here is, right, here's our line integral that Stokes Theorem said we should compute. And following our mnemonic to compute this thing, we do 1 over dt dt. And so here we see we just need our vector field f on the left. We do need the derivative of our parametrization on the right of the dot product, right? Derivative with respect to our parameter. And so here, I gotta scroll up a little bit. So here's our parametrization. Taking the derivative with respect to theta is going to hand us 0, -2 sine theta, and 2 cosine theta. And now we just need to compute the dot product like we would any other dot product, right? If we take the x components and multiply those, we get a nice 0. If we take our y components, multiply those, we get 2 negatives, giving us a positive z, 2 sine theta, and then similarly our z components give us what we see here, right? We're adding those up. There's no more vectors at all. We just have a scalar function after we compute the dot product. And now this integral that we're left with, right, it wants its variable only to be theta. We have a couple of artifacts, I guess, right? We had here we subbed in our vector field f, and this was the first time that that actually came up in our work. It's in terms of x, y, and z. We need to sub in for x, y, and z using what they are from our parameterization r hat, right? Looking at the x components, y components, and z components, we get our substitution equations, and we can plop those in where they go. And if we do that, we get a bunch of trig, and we can kind of combine some factors. We got 3 factors of 2 over here, 2 of 2 over here. And we're staring at this. Now we just have a nice clean single integral to compute. And we can just wonder how we would go about computing both these pieces. What about this sine squared over on the left? What could we do there? Well, we've got our double angle formula, right? Right, at least the sine squared, that equals, right, 1/2 1 minus cosine of 2 theta. So we can make that swap. We'd have still a 4 times out front. What about over here on the right? What could we use to integrate that? And actually in this case we could make u sine or cosine, and it'll work out, right? Just because either one's derivative is more or less floating around right outside. I'll leave the details for you to work out on your own. At the end of the day, what we get is 4 pi. So I want to play around with this example a little bit more. Let's keep the same vector field, but let's change the surface. All right, so we still have the same vector field f that we're thinking about. And what if instead of integrating the curl of that vector field over our ice cream cone, we just took this disk at the top of the ice cream cone and integrated the curl of our vector field over that, with this particular normal direction chosen. I claim we can see what we would get if we integrated the curl of our vector field over this new surface. Pause the video and see if you can think through what we're going to get and why. Okay, this is super cool, right? Surface integral for a curl field, this is what Stokes Theorem tells us about. And what Stokes Theorem tells us is, well, if we can either integrate this, or we can swap this out for a line integral, right? In particular, the line integral is going to be over the boundary of this surface, in this case, the same circle that we were looking at before. And, well, what direction are we going to be moving? Well, looking at this normal vector, right, if we do the kind of counterclockwise right-hand rule from it, that's going to be pushing us this way along our curve. And notice that is the same direction that we had before. So Stokes Theorem says that this surface integral for this new surface, right, integrating our curl field, we can swap out for the exact same line integral that we computed a few minutes ago. And so we'll once again get the same thing as we did then, 4 pi. And so here we see kind of a, I don't know, like the same theme that we saw with line integrals for gradient fields. How with gradient fields, right, once we had a starting point and an ending point chosen, right? We can move along this curve, or we could move it along some crazy curve. And we get the same thing. Right, when we're integrating a gradient field. Well, here, Stokes' theorem shows us that, well, if we took any other surface with the same boundary curve in pink, right, if we took this kind of this top of the ice cream cone, we maybe blew it up so it was coming out this way, but still had this curve as its boundary, we'd get the same thing integrating the curl of our vector field. And so because of that, because we'd get the same thing if we integrated the curl of f over any other surface with that same boundary, what we could say is that similar to how gradient fields are independent of path, curl fields are independent of surface. As long as you have the same boundary curve, integrating the curl of f is going to give you the same thing. That's it for today. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.